mathematical induction, or PMI, states that if we have a set S here that is a subset of the natural numbers, in the event that the set S would satisfy the following two conditions right here, that would be 1 is in S, and that if K is in S, that would imply as K plus 1 is still in S, then automatically set S here is just equal to the set of natural numbers here. Some of the books will have other presentation of PMI, and that is the one that we have here inside the box. For the benefit of others, let's discuss further this PMI right here. So let's have an outline of proving using principle of mathematical induction, or PMI. So first things first, we want to identify a set that would satisfy the given problem. So in that case, let's have S to be the set that satisfies this one right here. That means we have set S to have Note that in logic, we have to consider here an arbitrary integer. That's why we have to change the letter. So in this case, we change it to M. Now that we know our specific set to consider, that would be the set S here. Next would be satisfying the two conditions. So let's have the first condition. We have to show that 1 is in S. That means 1 should also satisfy the predicate here. A way to do that would be this. We have to verify that 1 here would indeed satisfy this part, or as I noted, if M is equal to 1, it should also work for this expression here. Writing that down, it would look like this. There, 1 can indeed be written as the form of this, which would be 1 times 1 plus 1 all over 2. With this, we are done showing the first condition. How about the second condition? Note that the second condition is in conditional statement. We have here K is an element of S. In that case, we are now to consider that K of them works in this series. Knowing that we have proven as well 1 being part of S, considering now K of them would mean 1, 2, 3, until K of them. Considering that this is your induction hypothesis, that it works for K of them, it would also mean that the numbers we have here, K of them, would also work for the series here. To picture that out, let's have that one at this part. So knowing that K works, it means that K would satisfy the predicate here. So 1 plus 2 plus 3 plus until K of them can be written as K times K plus 1 all over 2. So yes, this is our induction hypothesis. With this hypothesis, we are to show that K plus 1 element or 1 unit after K would still work in this predicate or would still be element of the given set S here. So as for the outline of the second condition, whenever you have this kind of problem, just extend the left side of your equation until k plus 1, and that will be achieved by adding k plus 1 to both sides of the equation and work algebraically with the given expressions. To picture that out, it would mean this. There. To have a detailed proof for this outline proof, just don't forget to click there at the top to be redirected to that video, alright? To widen our horizon, improving arithmetic series such as this using PMI, let's have an arithmetic series wherein we are not starting at 1, unlike the previous example. So to verify as well if you have gotten the gist earlier in doing the outline of the proof of PMI, let's have this. As noted, we have to denote a set that would satisfy the given problem here. So in that case, let's have set S to be this. There. After that part, again, we have to satisfy these two conditions here, starting with this condition that 1 is in S. So again, it means that if we are to enumerate elements of this set, we have to have 1 here as the start, or as noted, our final conclusion is that S would just be the same thing as the entire natural numbers. So it means that S eventually will have same elements with a set of natural numbers, so it would look like this. Alright, so for this part, let's start with the first one, of course, and that would be 1. Let's have that one here. So as noted, let's check if this would really work to each of them, starting with, of course, the first number here, which is 2. So yes, the first number there would actually mean as well the first number in set S. So that's how we do it, alright? 1 in S. 1 in S would always mean the starting point of the series that we're considering, which is in this case 2. Can we write 2 in the form of this? Since n is equal to 1, n equals 1 means the first element, 2 here, so that would be 1 times 1 plus 1. Note that yes, 2 here can be written as this form, wherein n is equal to 1, the first part of our series, 1, 1, 1 here, 1 here, plus 1 here, plus 1 there. This means that the condition 1 in S is satisfied. That is, n equals 1, or the first part of the arithmetic series, satisfies this expression here, or this predicate here. Alright? So I hope by now you have absorbed the concept of 1 in S. Common error is that if the series does not start with 1, the readers will be confused right away on how to start with the outline because they're used to having a series starting with 1. No, 1 in S here will just mean yes, we can enumerate 1 as an element of S, but in the same manner, 1 in S would also mean that the predicate here, or the given arithmetic series here, is being satisfied starting with the first element. Okay, so how about for the second condition? As noted, it would just mean that we wanted that, aside from us knowing that it works for the first part of the arithmetic series, or it works at the first element of letter S here, which is 1, we want to consider that it works to k of them. It means that aside from 1, it would also work for arbitrary k of them. And from then on, we are to prove that it would also work for 1 unit after k of them. So just like in our previous example, we'll have something like this. There. As being discussed earlier, if we are to put in writing this second conditional statement with this hypothesis, it would just mean that k in S would mean that k also satisfies the given arithmetic series. So in that case, this would also be true. As noted as well earlier, that for us to show k plus 1 in S, one easy way is to just extend the left side of the equation to k plus 1 of them. So it means that it should look like this. There. And notice that us adding this term right here, 2 times k plus 1, again this is 2 times k plus 1 because this would be the term after 2k. Common errors that others would think that after 2k is actually 2k plus 1. No, it would be that after whatever k is, that would be 2 times whatever k plus 1 is this time. As mentioned earlier, if you are to add this term at the left side, we have to add that as well to the right side of our equation. There. Extracting k plus 1 to that right side of the equation will have there. Now for us to show that k plus 1 would also work there, since we're already done with the left side here, what we want to work on this time would be the right side. We want that the right side must look something like, instead of k, it should now be k plus 1. So this would become k plus 1. This as well would also be k plus 1. And we still have the plus 1 there. There. So this left side should look like this to prove that k plus 1 is in S, or k plus 1 can really be written in this manner. Alright, so again, if you want detailed way of having this, then just click the icon there at the top. You will be redirected to an example of a detailed proof in doing PMI. So let's finish this up. So this would be k plus 1. Note that we already have that one here, and we want the rest of that expression to look something like this. And we can do that right now, because k plus 2 would be the same thing as k plus 1 plus 1. There you go. So this is still an outline of the proof. So again, when you are to prove, you have to have detailed proof, have wordings in it. So just base it from that detailed proof video that I've prepared for you. Alright, so thank you guys for watching. If you have some clarifications, feel free to inform me. Alright?